Good day, everyone. I am Bon Chow from SMK Convent Taiping. Let us learn the first subtopic of Chapter 7, Quantum Physics, which is the quantum theory of light. In this subtopic, we will learn about black body, ideas that spark the quantum physics theory, quantum of energy, and wave-particle duality. In Form 4, we learn about electromagnetic waves. It is made up of an electric field and a magnetic field that oscillate perpendicularly to one another, as shown in this picture. There are 7 types of electromagnetic waves: radio wave, microwave, infrared radiation, visible light, ultraviolet radiation, X-ray, and gamma ray. All these 7 types of electromagnetic waves form a continuous spectrum known as electromagnetic spectrum. This electromagnetic spectrum has increasing frequency from radio waves to gamma ray. All objects emit electromagnetic radiation. The cold objects emit waves with low frequency, for example, radio waves and microwave, while the hot objects such as sun emit waves with higher frequency, for example, visible light and ultraviolet radiation. What is black body? It is an idealized body that is able to absorb all electromagnetic radiation that falls on it. The picture here shows a black body. When there is light ray enter the hole into the black body, this light ray is being reflected again and again from the inner wall until it is absorbed fully by the black body. Black body can also emit thermal radiation depending on its temperature. Thermal radiation is electromagnetic radiation that includes the radiation that human eye can see, for example, visible light. It also includes the radiation that human eye cannot see, for example, infrared radiation. The radiation emitted by the black body forms a continuous spectrum, and it is unaffected by the nature of the black body surface. Continuous spectrum in this figure shows a spectrum of visible light. Black body radiator. What is that? It is an object that emits electromagnetic radiation determined by its temperature. The examples of black body radiator are sun and hot metal. Yes, indeed, sun, it is an hot object. It emits electromagnetic radiation. Hot metal, when a metal is being heated, it will emit radiation as well. This diagram shows that the air cavity acts like a black body. When there is a light ray enter the air cavity, the light ray will undergo reflection repeatedly in the inner wall until all the light rays are absorbed by the wall. Thus, air cavity is a black body. When an object is being heated, the temperature will become higher and higher. The object acts as a black body radiator and emits thermal radiation. I give you an example: hot metal. If you heat up a metal, the temperature of the metal will become higher and higher, hotter and hotter. Now, the hot metal is a black body radiator and it will emit thermal radiation. Yes, we can feel the heat. Over here, there is a graph of radiation intensity against wavelength for 3 types of black bodies: the red stars, white stars, and blue stars. How do we analyze the graph? We will read the graph from the right side to the left side. On the left side, this is an area with short wavelength. On the right side, it is an area with long wavelength. As you can see, when the temperature of the black bodies increases, like this, what happened to the wavelength? The wavelength is become shorter and shorter. So, the higher the temperature, the shorter the wavelength, approaching the maximum radiation intensity. And the higher the light intensity of a black body, the more light energy it emits. Examples of black bodies in daily life. As we all know, black body can emit thermal radiation depending on its temperature. The higher the temperature, the higher the thermal radiation. And the radiation emitted forms a continuous spectrum. This is a spectrum for visible light. What color that we can see? We can see red, orange, yellow, green, blue, indigo, violet. Look at this picture. It is a picture of hot metal. Hot metal is a black body. It means that this hot metal can emit thermal radiation. And the radiation emitted will form continuous spectrum. What do you see over here? What color that you can see? I think I can see yellow, orange, red. Wow, this is the radiation emitted. The other examples are like thermographic image of a car, oven heating element, and thermal radiation in light bulbs at different temperature. Now, we will learn the ideas that spark the quantum physics theory. The ultraviolet catastrophe, also known as the classical theory, says that the electrons vibrating at the same frequency should have the same energy content, and the vibration of electron has no limit. The light energy produced by the vibration of electrons can reach unlimited high values. Remember how we analyzed the graph? We analyzed the graph from the right side of the graph to the left. So look at it. The light energy produced or the radiation will reach unlimited high values according to classical theory. However, the experiment result shows that when the radiation reaches the peak, the radiation does not continue to increase when the frequency increases. What happened to the light intensity? It starts to decrease. So, the experiment result and the classical theory, there is a controversy. And that controversy sparked the quantum physics theory. This is the development of quantum theory from classical theory. Thomas Young conducted double-slit experiment. We had learned this in Form 4, and it shows that light is a wave. Light wave is a continuous spectrum. But he was unable to explain the radiation spectrum produced by black bodies, while John Dalton was unable to explain the light spectrum produced by atoms. J.J. Thomson was unable to explain the light spectrum of light produced by atoms. This is the development of quantum theory, started by Max Planck. He introduced the concept of quantum, which is discrete energy, that actually solved the controversy from the graph that we saw just now. Followed by Albert Einstein. He introduced the photon concept and his Einstein quantum theory of light was successful to explain the characteristic of photoelectric effect that could not be explained by the classical theory. Niels Bohr explained the production of light spectrum by hydrogen atom, while Louis de Broglie postulated the idea of wave-particle duality. After we see the development of quantum theory from classical theory to quantum theory, we know that electromagnetic spectrum might not be only continuous spectrum. It could be a light spectrum as well. In classical theory, Thomas Young conducted an experiment, the double slit experiment. It shows that light is a wave. When you have light wave pass through a prism, the dispersion of white light produces a continuous spectrum that consists of 7 visible colors. This visible light spectrum is a continuous spectrum because, as you can see, there is no separation gap between each color in the spectrum. In quantum theory, Niels Bohr explained the production of light spectrum by hydrogen atoms. An excited atom will produce a series of color lines with unique wavelength and frequency, and each element produces a spectrum with a series of its own distinctive lines. It means different element, different light spectrum. Therefore, the light spectrum can be used to identify the presence of an element. This diagram shows the difference between continuous spectrum and light spectrum. Continuous spectrum is produced by white light, while the light spectrum is produced by excited atom. What is quantum of energy? It is discrete energy packet and not a continuous energy. The energy depends on the frequency of waves. According to Max Planck and Albert Einstein quantum theory, light energy exists in a form of energy packet known as photon. So light energy is a photon. Photons are light energies transferred in quantum of energy. The symbol E represents photon energy, while symbol F represents the frequency of light wave. Photon energy is directly proportional to frequency. It is related to one formula, which is E equals to hf. H is Planck's constant, and the value is 6.63 times 10 to the power of negative 34 joule second. In this table, it shows you that the higher the frequency of light waves, the higher the energy quantum. Electromagnetic radiation such as light have wave properties or wave characteristics because it can show us the phenomenon of diffraction and interference. Objects like marbles are said to have particle properties because it has momentum and kinetic energy. It can also collide with each other. Louis de Broglie introduced an hypothesis which is all particles can exhibit wave characteristics. However, in the experiment, it doesn't work. The particles with large masses difficult to show the wave characteristics. So he predicted that only light particles, for example electrons, can exhibit wave characteristics. He introduced a formula to relate momentum of a particle and its wavelength, which is lambda equals to h over p. Lambda is wavelength, h is Planck constant, while p is the momentum of particle. Simply because momentum equals to mv. We learned this in Form 4. Thus, this formula can be written as h over mv as well. Based on this formula, lambda equals to h over mv. Have a look. H is Max constant. It is 6.63 times 10 to the power of negative 34. If you use a very small value to divide a very big mass, okay, a very big mass, you will actually get a very small value of wavelength. So, since the value of H is very small, the particles of large masses will have the wavelength which is too short to be detected. We cannot detect those particles with large mass. What is the wavelength for them? Now, look at the picture on the right. This is an experiment that we have learned in Form 4 syllabus, the experiment of diffraction of light waves. And this is the result. On the left is the result of electron diffraction experiment. Look at the pattern. Compare them. Do they look alike? Yes, both patterns look alike. Simply because from the electron diffraction experiment, the result, the pattern shows that it look alike with the diffraction pattern of light wave through an aperture. This confirms the hypothesis of de Broglie is correct, which is all particles can exhibit wave characteristics. Do you remember just now we talked about the de Broglie's wavelength is too short to be detected? Thus, something needs to be done. The de Broglie wavelength for an electron beam is approximately 1000 to 10,000 times shorter compared to the wavelength of light. Because of this property, we need to use something else, which is the electron microscope, to get higher magnification of the image. This picture shows you the comparison between the images produced by optical microscope and electron microscope for red blood cells. So obviously, by using the electron microscope, we can see a higher magnification of the image for red blood cells. From all that we learned just now, we know that electron exhibit particle properties and wave properties. Same goes to light. It exhibits particle properties and also wave properties. Therefore, we say that both light and electron have wave-particle duality. This duality is also found in all radiations, in electromagnetic waves spectrum, and also subatomic particles like protons and neutrons. Do you remember what is the first formula we learned in this subtopic? That is E equals to HF. E is photon energy, so this is applied in photon. This formula also can be applied in electromagnetic waves after we learn about wave-particle duality. But before that, we have to understand the characteristic of electromagnetic waves. It moves with speed of light. Symbol for speed of light is a small c. Formula for wave speed is v equals to f lambda. So we are about to change the small v to become small c because electromagnetic waves move with speed of light. So then we get it f equals to c divided by lambda. So we are about to substitute f equals to c over lambda into photon energy formula. Okay, all remain except f is changed to c over lambda. So you have E equals to hc over lambda. Okay, next one. There's another formula introduced to you for calculation purposes, that is photon power. It is equivalent to NHF. So we can also write it as NHC over lambda. So this photon energy and photon power can be used for calculation purposes. That is all for 7.1 Quantum Theory of Light. Thank you.